Hello, welcome back. In this video, we're going to continue our notes on the fundamental theorem of line integrals. We talked in a previous video that if we know a vector field is conservative, then it's independent of path. Therefore, regardless of path, the line integral is going to be the same. And in many cases, this is going to be easier for us to use the fundamental theorem of line integrals. So in the following examples, we are going to evaluate the line integral. Given the following vector field, y squared 2xy, we want to see how that vector field will affect the following four paths. So before I try to make these into a parametric, which these are going to be pretty ugly, for this one to be parametric, I'd have to do two paths here, a circular path here, I'd integrate a circle, which is never nice, a closed path right here, and this one has four different paths we'd have to evaluate. And that could take a long time. But let's see if this is conservative. So if this is conservative, our rule is simple. Here's m, here's n. We want to make sure that the partial of n with respect to x is equal to the partial of m with respect to y. So we're looking y with respect to y. If we were to bring the partial of n with respect to y over, we would get the partial of n with respect to x minus the partial of m with respect to y. And if you're thinking this looks like the curl for three-dimensional vectors, you're pretty much correct. But this is the curl for a two-dimensional system. In other words, we're saying that it is irrotational. It's not moving, and that's what the curl means. And if it's not moving, we're saying, well, it doesn't matter. So that vector field is not moving, if there's no rotation to it, we're saying that the vector field is conservative, and we can use the fundamental theorem, the line integral. Because if it's conservative, the rule is we can find the potential function. And that's what we want to find first. We want to find the potential function. Well, my potential function is pretty darn easy to get. If we look at the x's, we saw this in the previous videos. There is my x component. I want to integrate that with respect to x. So I would take this y squared, integrate that with respect to x, and we would get y squared x. Again, plus some constant with respect to y. And I do the same thing with the y's, but this is going to become 2xy dy, which again is going to become just y squared x plus some constant with respect to x. So our potential function is just going to be this xy squared, and there's plus some constant, but to use a fundamental theorem, we only want to get the original function. Now, remember, this comes from Cal 1. If I can find the antiderivative, remember, the potential function, the vector field, comes from my gradient, which is just a list of my derivatives. Given those derivatives, we found the function that gave us all of those derivatives. And now we're just going to evaluate that. So for part A, we are going to take our potential function, xy squared, and our evaluation, we're going to go from 0, 0 to where we ended, 4, 4. So in other words, what we're saying is, as long as I start at 0, 0, end at 4, 4, because it's conservative, I can follow this path, or I can go any path I want. I can take the long way home. Now you gotta be careful though. That I can do, but this I can't, because that becomes what we call a complex path, because I cross this up. We don't want to do that. All right, so evaluating this, plugging in the 4, 4, that becomes 4 times 4 squared minus 0, because 0 times 0. And that's just 64. Much easier to do than using parametrics. To do a parametric, man, we'd have to take a look at all those different paths. Sorry about that. All right, for part B, I'm going to take that same one, xy squared, and I'm starting at negative 1, 0, and I'm ending at 1, 0. Plugging those in, that's going to give me 0 minus 0, so we get 0. That was no work at all. Get it? No work, because we're looking for work, and we got 0. Anyways, moving on. Here, take our path. We get x, y squared. Now, this one should be pretty easy. They don't really tell us where we start, so we'll start at 2, 2. So I'm going to go from 2, 2. As I go around the path, we start at 2, 2, and we end at 2, 2. Now, we should know from last year, there's a rule for calculus. If we start at A and end at A, that's going to be 0. So that's pretty easy. So this is a conservative closed vector field. And what this is telling us is, hey, if we start and end at the same place and it's conservative, the vector field is going to be 0. The same thing for D. Let's take a look at D. If I take that vector field, if I start at, if I say we start at that 1, 0, we're going to end up at 1, 0, and we get 0. So, and that's what this says. For C and D, both end up having a value of 0. The vector field, or it's our line integral, is just 0 for every closed curve C if conservative. All right. Hope you enjoyed this video. Please go out and have some fun. We'll see you next time. We'll talk about Green's theorem.